Hello, and welcome to demola. And today we are working through OCR 2014 Chemistry Paper 3. The last of the lot, 70 marks. Let's get straight into it.
Okay, so our question here, we're talking about acids, bases, and salts. So pH of 1 decimeter cubed of 0.4 mole per dm cubed of sodium hydroxide. So we should know our Kw formula is equal to the concentration of hydrogen ions multiplied by the concentration of hydroxide ions. Cool. And also from your data sheet, you should see Kw at 298 Kelvin is 1 times 10 to the minus 14. So what we're going to do is we're literally just going to apply those values. If we're working out pH, we need the concentration of protons, right? So we know that that is going to be equal to, if we rearrange, Kw divided by the concentration of hydroxide ions. Now, I'm just going to input our values. So 1 times 10 to the minus 14. And then also we're going to do the 0.4, because you can see here, if there's one hydroxide in that much concentration, then that's what we're going to get. So when we do that, we get 2.5 times 10 to the minus 14. And then we can just do minus log pH of 2.5 times 10 to the minus 14. And that will give us an answer of 13.60 as our pH. Cool. Now they're saying what's the pH of a diluted HCl, and I just always kind of look at this, 2 decimal places. So that will tell us how much we want to give our answer to. Now I can see the change in the volume is by a factor of times 10, which means the concentration is going to go down by a factor of times 10, or down by a factor of 10. And that's just what you need to know. So I'm going to do 0.75 divided by 10. We get 0.075. And I'm just happy to do the minus log of 0.075. And that should give us our answer. So doing that, we get a pH of 1.12 to 2 decimal places. Okay. Finally, what we're looking at here is, okay, we have a weak acid, right? So I know, just quickly doing a formula for Ka. Ka is equal to this times concentration of A minus over concentration of HA. So again, if we're working out pH, we want the concentration of protons, right? So I'm looking, we've got our Ka value here. This one is going to be for A minus, and this one is going to be for HA. Hope that makes sense, because that's your acid and that's your conjugate base. Yeah. So let's just put in our values. So first, if we arrange for H plus, we're going to get Ka over Ka multiplied by Ha over A minus is equal to H plus. So if we just put in our values, and again, I'm just looking 2 decimal places again. So we're going to get 1.75 times 10 to the minus 5 multiplied by Ha, which was 0.3, divided by 0.1. So when we do all of that, what we're going to get is 5.25 times 10 to the minus 5. And then again, we're just going to do the minus log of 5.25 times 10 to the minus 5, which is going to give us a value of 4.28 to 2 decimal places. Okay, so for these type of questions, after you've read it, just realize when it says given quantities, apparatus, and method, specifically the quantities, it means that it wants you to do a calculation. So we're going to need to calculate how much copper we need for this process. So in order to do that, we're thinking, okay, I've got the concentration, I've got the volume that we want. So to get the mass, we need to know that moles is equal to concentration multiplied by volume. So we're going to do that. So let's do the 0.2 multiplied by the volume. This is in centimeter cubed, so in decimeters cubed it's 0.1. We're going to get 0.02, yeah, moles. And then moles multiplied by molar mass is going to be able to get our mass, right? So with this 0.02, we're going to times it by the MR of this whole compound, which you're thinking, okay, 63.5 is copper, plus nitrogen is 14, there's 2 of them, so 28, plus oxygen, there's 6 of them, so 16 times 6, 96, plus whatever 18 times 3 is. And that's going to give us 241.5. So that multiplied by 241.5 is going to give us a mass of 4.83 grams. Cool. And the reason why we're going to do 2 decimal places is because you'll notice most of the weighing scales we use in school have 2 decimal places. So just leave it at 2 decimal places. Now, in terms of the method, this is important. So again, we're using the value we got. So weighing out the 4.83 grams of your hydrated copper nitrate, yeah, using a measuring boat. So I'm going to highlight things I think are important. That's apparatus, which I told you to use. Cool. Now, we're going to pour that into a beaker and dissolve using distilled water. Yeah, another really important point, we'll highlight this in a different color. They love it when you say rinsing out. So when I say we're going to rinse it out, yeah, Then we're transferring it into, because we're making an 100 centimeter cube solution, so an 100 centimeter cube volumetric flask. And again, remembering, rinsing out the beaker. Now, in case you don't know, this is what a volumetric flask looks like. So it's kind of got that like kind of pear-shaped thing at the bottom. And this mark is going to be at 100 centimeter cubed or 250 centimeter cubed, whatever one you're using. Fill it up to the line, and then another really important method point is about inverting the flask several times to mix it. So that's your method, that was your calculation. And you can see here we've used quantities, we used apparatus, and we've also used method. So that's how you're going to get the marks for that. Okay, so looking at this question, we're talking about bond enthalpies now. So first of all, they're saying, why do all average bond enthalpies have a positive value? Well, it's because bond enthalpy, if we define it, is the energy required to break covalent bonds, right? So that's an endothermic process, which is why we're going to say that all of them are positive because they're all endothermic now. Okay, to do this, first of all, I really do like kind of drawing out what I'm seeing in the equation. So we're just going to draw it out. So we've got methane, which is this. Then we're adding water, which is that. And then it's going to hydrogen, 3 lots of this, plus carbon monoxide. So that's what we've got, and we can apply the bond enthalpies that we have to that. So I'm saying we don't have CH, which is what we want to find out, but there's 4 of them, so 4x. This is going to be 2 lots of 464. This one is going to be 3 lots of 436, and this one is going to be 1077. So we're just thinking, okay, this is going to be reactants minus products to get our bond enthalpy, to get our like enthalpy change of reaction. And the reason why we say that is because if the products is going to be exothermic or your bond making, if there's more energy there, then it's going to be negative. So if we have more energy in the products and we're taking it away, that's why it's going to be more negative. So what we want to do is just make an equation. So we know our enthalpy change is 195. So 195 is going to be equal to 2 times 464, which is 928. 928 plus 4x. And then minus, I'm just going to literally add the 3 times 436 is 1308 plus the 1077 is 2385. So we add it. So we're going to put it to the other side, 385. We get 2580 equals 928 plus 4x. And then take away the 928. 1652 is equal to 4x, which means if we divide it by 4, we get an answer of 413 kilojoules per mole. And we can say positive, but we know it was going to be positive. So that's going to be our answer there. Now, for this one's a bit more difficult, but we're thinking, okay, it says room temperature pressure, and we're dealing with a gas, hydrogen gas, yeah? So that's a hint that we're going to have to use our ideal gas equation. Cool. So knowing that, what we can think about, okay, so we have our volume, but it's in meters cubed, which is important. Look for your units. So we need to do 60 multiplied by 10 to the 3, divided by 24, and that will give us a number of moles. So when we do that, we're going to get 2,500 moles of hydrogen gas. Now, when I'm thinking about the enthalpy change of formation, that equation is going to be hydrogen gas plus half of an oxygen molecule is going to form water. So if you see the molar ratio, it's 1-to-1 between hydrogen and water. So because this is a kilojoules per mole, we're happy to use that value, the 258.8, to find the energy that's going to be released, yeah? So we're going to do the 2500 multiplied by 285.8. Don't worry about the negative because we're just doing energy released, which is a scalar quantity. So that's going to give us 7.15 times 10 to the 5, which is going to be our answer. So 7.15 times 10 to the 5 kilojoules. Okay, so we're told that compound A is a chloride of a period 3 element. So already just think towards period 3. You have a periodic table with you in the exam. Now, we see step 1, we see step 2. So in step 2, they're saying we're forming a white precipitate with your silver nitrate, which is obviously going to be silver chloride. So when we're dividing the ionic equation, this is one that literally you should just kind of know anyway. You can suss it out through this, but really you should know. This is Ag plus, which is aqueous, plus Cl minus, which is also aqueous. And that goes to form the solid precipitate, silver chloride. And because it's a precipitate, it's solid. Cool. But that's an equation that I just recommend learning. Now, in terms of the formula for compound A, this is a bit more difficult. So I'm thinking, okay, we have what the moles of compound A is. We need to think, what is the moles of our silver nitrate, and then that will help us to find a ratio, which will give us what the element is from group A. Cool. So just thinking about from period 3 for group A, for compound A. So I'm thinking, okay, the best way to do this, well, we know, we've done this before, moles is equal to concentration times volume, and we have a concentration and volume. So if moles equals concentration and volume, we can do 2.5 times 10 to the minus 2 multiplied by, and again, we're going to change it to decimeters cubed, so times by 0.06, and what you're going to get is 1.5 times 10 to the minus 3. Okay, now we've got that. We had before it was 5, so I'm going to do my ratio, 1.5 times 10 to the minus 3 and 5 times 10 to the minus 4. If we divide by the smallest value, so I'm going to do the 1.5 times 10 to the minus 3 divided by 5 times 10 to the minus 4, and I'm going to get 3. So it's a 3 to 1 ratio. So what we're saying is there's 3 chlorides to whatever this element from period 3 is. Now, by our hints of deduction, we realize that means it's in group 3. If it's in group 3, then the only logical solution is that that's aluminium. Yeah. So just making the formula for compound A, it would just be AlCl3, and that should be your final. Okay. So for part 1, no easy way to do this. We literally just need to count. So I'll start with the carbons. We're gonna count them up. You got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So we're gonna get C13. Let's count the hydrogens now. So this is a bit more difficult, but we got 1, 2. I'm just gonna rub out the other ones I did. I would maybe do different shapes in the exam. But 1, 2. That's using all its bonds. This one has 1 here. This one, by the same logic, also has 1. This one doesn't have any. Cool. Keep it moving. This one is gonna have 1. That's 1 there, and it should have another one as well here. Same here. And then this one is gonna have 1. So this one has 1, 2. This one doesn't have any. Yep. This one has 1. This one has 3, and this one has 3. So just counting up 1, 2, 3, 4. Oh my goodness. 5, 6, 7, 8, 9, 10, 11, 12, 13, and then 13 plus 3 is 16, 19. So there's 19 hydrogens. Cool. Working it through. So now we've done all the hydrogens. Let's do nitrogen next. So nitrogen, we can just clearly see there's 3 of them. So 3 nitrogens, and then oxygen, we've got 1, 2, 3, 4, 5, 6, 7 of them. So that's going to be our molecular formula now. In terms of chiral carbons, we need to first of all know what is a chiral carbon. So a chiral carbon is when a carbon is attached to 4 completely different groups. So first of all, we can immediately say it's not going to be any of them that have a double bond. So we can ignore those carbons. So let's look at the other ones. So this carbon is attached to nitrogen, oxygen, this carbon chain with a oxygen, and then a hydrogen. So this is one of them. This one, similar thing, is attached to a carbon chain. It's attached to this carbon chain, which are different. It's attached to OH group and hydrogen. So that's the second one. Same logic, that's the third one. And this is the fourth one because you've got carbon chain, oxygen, hydrogen, and a different carbon chain. So there should be 4 chiral carbons. This one has 2 hydrogens, so no. This one has 2 CH3 groups, so no. So we're going to say there's 4 chiral carbons. And then in the synthesis of the compounds C and D, we can see here that it says the nitrogen in compound B is replaced by phosphorus, and in D, oxygen is replaced by sulfur. So if we found the difference of the relative molecular masses, I just thought, okay, easiest way is, let's look at compound B. What's the molecular mass? 329. So in C, we said that we removed the nitrogen and replaced them with phosphorus. So if we do the 329 minus 13 lots, so 3 lots of 14, what are we going to get? So 329 minus 3 lots of 14, you get 287. And then if we just add on instead now 3 phosphorus, so phosphorus is 31, I believe. So plus 3 times 31, you're going to get 380 is the new one here. Here, similar thing. So 329 minus, we're taking out all the oxygens this time. So 7 lots of 16. So if we do that, 329 minus 7 lots of 16, you get 217. And then now we're going to add 7 lots of sulfur, which is 32.1. Make sure the decimal's clear. So plus 7 times 32.1. And we're going to get 441.7. So then now we just find the difference. So 441.7 take 380 should give us an answer. And that answer is going to be 61.7. Okay, so first of all, we're working with ether diarrhea ions, which is a bidentate ligand. Cool. So in terms of defining a ligand, we know a ligand is a species that donates a lone pair of electrons to a central metal ion, forming covalent dative covalent bonds. Right. Now, if it's bidentate, it means it's forming two dative covalent bonds. So that's what you just need to say. So it donates its lone pairs to a central metal ion, forming two dative covalent bonds. Cool. In terms of this one, we know the shape is octahedral. So we know there's going to be 6 bonds around the ion. Now, what is just really important is we know it's an Fe3 plus, right, based on that. And if we're going to form 3 of these, we just need to know what the charge of our complex ion is. So we're going to have the +3 and the -6. So overall charge is going to be -3. Cool. Now, in terms of drawing, right, this is the difficult part. And with the arrows, unfortunately, you just kind of need to know where they go. So if this is the iron, then what I'm saying is, okay, we're going to have a bond up here. We're going to have a bond kind of, I like to do it like this, going into the page away from us here, which is bound to another oxygen. We're going to have a bond here, which is coming towards us or out of the page. And that's going to be here. And I have another one in line here. Another one that's kind of going out of the page towards us here. And then finally another one that's kind of coming away from us here. Hope that works. So that's something that you just need to know. And then finally, we're just going to kind of finish off the molecule. So we know what if and di what it looks like if we just have another look. So it's going to be carbon to carbon and a double bond. So I'm just thinking, okay, best way is if we kind of go inside here. So this is a carbon, that's another carbon, and then double bond. Again, it doesn't have to be perfect, but you just kind of need to get the general gist of what's going on. So this is another one. And we're going to come with the carbon to double bond O, double bond O. And then this one again, these two are going to come in together, carbon, and then double bond O, and double bond O. And then I'm happy to kind of wrap that up and do a 3 minus. And then you need to draw a mirror image of that. So you literally draw a mirror image. So I'm thinking, okay, quickly, Fe. So in terms of the mirror image, this time, this one that we're going to label 1 is now going to be facing like this. So again, it's going to be a bond coming out of the page, as so, and a bond going into the page, as so. Cool. This one is still going to be up here. This one's now facing the other direction. So that's an O. And then these two, again, so we had one that was going on the same plane as the page here. And we had one that was going, no, so I'm just looking at what it is. Yeah, this one is, yeah. There we go. Oh. And this one is O as well. So yeah, that's going to be our shape, and then we just need to join it up together. So you can see we're drawing a mirror image, and again, carbon to carbon, double bond O, double bond O. So again, I'm not going to lie, I'm not the best drawer, but you literally just kind of need to show the bonds. That's what they more care about. Where are the bonds going? Are the bonds going to the right places? And if so, that will help you to get your marks on this question. So you can see here, I'm not a good drawer. 3 minus there. And yeah, that's what you do. Okay. So in terms of oxidation reactions, the first one shouldn't be too bad. So if we oxidize, we're obviously losing electrons. Yeah, oxidation is loss of electron, reduction is gain. So if we have Fe2 plus, as it says, thankfully we don't need to use state symbols. So going here, we're now going to be Fe3 plus, and we're also going to be plus E minus. Cool. Now, in terms of this one, if we're oxidizing this one, C2O4, 2 minus. What I'm thinking is it's probably going to form carbon dioxide. That's just the most realistic kind of solution. So we're going to have CO2. So when we have CO2, I just remember there's 2 of them because there's 2 carbons. And that also helps us with the 4 oxygens. Perfect. And then we're going to add the 2 minus because we had the 2 minus charge. Okay. This question isn't too bad. So you do get questions like this a lot. So literally, you have to just read off the value. So what you should know is you're reading from the bottom of the meniscus, so like here. So when we're going down, we can see that's like 23 point, I wouldn't necessarily go 23.6 yet, it's more like 23.55. So that's what we're going to put on our table, 23.55. And that is allowed. So 23.55 here. And the initial reading on here is probably about 1.9 on the dot. So I'm happy to say 1.90. And then we're literally going to do that across here. So I'm just going to kind of just put in the answers just because it will save us a lot of time. And then all you have to do from here on is literally just do final, take initial, and that'll give you a titer value. So titration is a practical that you should have done, which is quite important to do in 21.55. Okay, that's that done. Now, in terms of uncertainty, what you need to realize is, okay, we wanted uncertainty for the titer. We took 2. So we took 2 measurements. So it's going to be 2 multiplied by the uncertainty, 0.05, divided by what the titer value was, 21.65. And if we multiply that by 100 to get a percentage, you'll get 0.46%. Okay, so titration calculations are difficult, but we're going to work through it step by step and hopefully help you get to the right answer. So first of all, what we need to look at, okay, what was our mean titer? So we need to remember use concordant values, meaning they're within 0.1 of each other. So we're going to use titration 1 and titration 3 to get our concordant titers, yeah? So our mean titer is going to be the average between the 21.65 and the 21.55. We can do the calculation properly, but we'll just say mean titer. So about my handwriting, it goes off when I write first. But it's going to be 21.60 centimeters cubed. Okay, fine. Now, when we looked at our titration, we were doing it against 0.02 moles per decimeter cubed of manganate, potassium manganate. Cool. So, given that information, that means that we can now find the number of moles of manganate because we have the concentration and we now have the volume in the mean titer. So we know that moles is equal to concentration multiplied volume. So we'll just do that. So if moles is equal to concentration times volume, then that means we can do the moles of the manganate ions is going to be equal to the concentration of 0.02 multiplied by the volume of 0.0216. Remembering that we have to do it in decimeter cubed, not centimeter cubed. So then we're going to get 4.32 times 10 to the minus 4 moles. Cool. Now they told us that it was a 3:5 ratio, right? So given it's a 3:5 ratio, I'm going to do this 4.32 multiplied by 5 over 3, which is going to get me to 7.20 times 10 to the negative 4 moles of our ethane diarrhea ions. Yeah? Cool. Now, what you need to realize is we were titrating 25 centimeter cubed, but the solution was 250. So we need to times it by 10 because it was in 25 and because we want the 250, but we did 25 centimeter cubed. So we times it by 10, so we get the moles in the 250. Yeah? So the moles of FeC2O4 is going to be equal to 7.2 times 10 to the negative 3. Okay. So now you've got the moles. Now we need to think. We want to find the value of X in the hydrated salt. So we need the molar mass. That's going to be the most important thing we can calculate, the molar mass. So we know that molar mass is going to be equal to, if we rearrange some equations that we know, mass divided by moles. Yeah? So we have the mass 1.295. So 1.295 divided by the moles, 7.2 times 10 to the negative 3, is going to give us our MR, which is going to be about 179.9. Okay. So now that we have that, we need to think, okay, we just want to find the water part, right? So we need to take away this first bit, the iron ethane diarrhea part. So 179.9 minus, and if we just quickly do on the top of our head, so I'm going to put this in my calculator. We just need to add it up. So I believe it should be, I think 58.8 is iron, plus 24, plus 64. And that's gonna, oh, it's not 58, is it? Okay, I think just overall, I've got 143.8. Yeah, that's basically what I've got. Yeah, so 179.9 take 143.8 is gonna be 36.1. If we do 36.1 divided by the MR of water, which is 18, we get 2.0056 basically. So I'm just happy saying X is equal to 2 pretty much. It's not always that X is going to be a whole number. Just be aware of that. It's not always going to be a whole number. In this case, it is, but there are chances that it won't be. So x is 2. That's how you work. Okay, so for this one, we're looking at the equations. We're just talking about phosphorus here. Yeah. So it says that during the equilibrium, H2PO4 minus acts as an acid and a base. So we first of all need to define what is acid and base. When acid is a proton donor, a base is a proton acceptor. So we need to see where this molecule specifically is acting as both. So what I'm going to do is I'm going to highlight where we see the molecule. We see it here, and we also see it here. So as you can see in equation 1, it's accepting a proton to become H3PO4. In this one, it's now donated a proton. Yeah. So in that essence, in 1, it accepts a proton and acts as a base. In 2, it donates a proton and acts as an acid. That's what you want to say. Now it's saying in a H3PO3 molecule, the oxygen is covalently bonded to the phosphorus and the hydrogen is covalently bonded to the oxygen. So given that our main character at the moment is phosphorus, I'm just going to draw phosphorus in the middle here. So we draw phosphorus, and they said the oxygens are all covalently bonded to that. So I'm going to do one here, one here, one here. And then they've said that the hydrogen is bonded to that. So bam, bam, and let's go with bam. So we should be happy with that. Now, in terms of our knowledge of bonding, going back to module 2, what we should know about phosphorus is in group 5, right? So it has 5 electrons in the outer shell, meaning that it has a lone pair of electrons. Yeah. So we need to know what is the bond angles here. So this one, bam, is going to be 107 degrees because it's trigonal planar because it's 3 bonding pairs, 1 lone pair. And then this one here is going to be 104.5 degrees because oxygen has the 2 lone pairs as a central atom. Yeah. And because of that, you form a bent shape. Cool. Then in terms of systematic naming for this compound, what we're thinking, okay, we need to know the oxidation states. And for oxygen and hydrogen, thankfully, they stay kind of similar. So oxygen is -2, hydrogen is going to be +1. And we have 3 of each. Yeah. So this is -6, this is +3. So we're thinking, okay, it's obviously a neutral compound, right? So overall the oxidation is 0. So to bridge the gap here, we need to add 3. You have to bridge the gap between -6 and +3. To get it to 0, we need to add 3, which means our phosphorus has an oxidation state of 3. So we're going to say phosphoric, and then in Roman numerals, 3, and then acid. And that should be the answer. Okay, so phosphine is a poisonous gas, reacts with oxygen to form phosphorus oxide and water. Cool. So in terms of that equation, this is going to be the hard part, finding an equation for that. But I'm just thinking, okay, phosphorus has an oxidation state of 5 as dictated there. Oxygen is always -2. So I'm just kind of thinking, okay, lowest common multiple is going to be our best bet here, which is 10. Yeah, so we're going to have to times oxygen by 5, phosphorus by 2. That's the easiest way of doing it. So if we say it's going to be pH3 plus O2 going to P2O5 plus H2O, that's going to be our best bet. And then we can just do, this doesn't seem too much of a complex equation. So we're going to do left hand side, right hand side. We have phosphorus, hydrogen, and water. So we've got 1, 3, 2. We've got 2, 6. So 2 and 6. Okay, so now I'm just thinking, okay, let's just balance what's a bit simpler first. Now, I can see there's on the right hand side more compounds that contain oxygen, so I'm going to leave that to the end. So if we do phosphorus first, I'm going to need to times this by 2. Yeah, so times it by 2 and we've got it balanced. And now this has become 6 now. So then we need to times this by 3. And then when we times it by 3, we got 3 plus 5, 8. So this is now 8. And then that means that we just need to put a 4 here and it's balanced. Cool. Now, in terms of this one looks like insanely difficult to balance. So we're going to do it based on oxidation states, which is, again, like I think that's why it's hinted at in the question. It will be a bit easier. So I've written all the oxidation states of the elements here. And you can see this is done a -1. This is done a +6. So you can see here that essentially for every mole of phosphorus, or for every electron phosphorus gains, then silver has to lose. Does that make sense? No, sorry. It's phosphorus loses 6, silver gains 1, basically, is what we're saying. So the 6-to-1 ratio between silver and phosphorus. So that's what we kind of need to make clear. So that means here, we need to put a massive 6 here. Yeah? Cool. We put 6 here. We're happy with a 1 now. from here, we should kind of be able to balance it. So we're thinking, okay, silver's going to have a nice 6 next to it. Let's balance the nitrogens now. So on this side, we've got 6 nitrogens. To get 6 nitrogens, I'm going to have to put a 6 here. Cool. In terms of the oxygen, that's in 2 compounds. So I think what might be next is just seeing what we've got. So literally on this side, in terms of oxygen, we've got 6 times 3, 18. We've got 19 there, which isn't a great number to use. And then here on oxygens, we've got 18, we've got 21. Okay. So I'm going to leave that for a second and see if maybe balancing the hydrogens is going to be a bit easier for us. So I've just forgotten this has to be a 1 as well, just because of the phosphorus. So actually, if that side's completely balanced, then we only need to balance this. So let me just quickly look at the hydrogens, but it's going to mean that we're going to need 3 more. Because if there was 18 on this side, or 9, then that means we're going to need to make it 21. But I'll just double check as well with the hydrogens due process. There's going to be 9. So on top of this one, which is 3, we needed 6 more. So yeah, 3. I hope that makes sense in terms of balancing it. I know I haven't actually written it all out, but I hope speaking through it made sense. So what we said is that we had a silver reduced from +1 to 0. And we also had phosphorus was oxidized from -3 to +3. So in that case, that's why we have a redox reaction, yeah? We have oxidation and reduction happening in the same equation. That will be fine for you. Okay, some more equations to do. So in terms of writing this one, we know PCl5, so PCl5 plus ammonium chloride, which we need to know. So ammonium chloride, NH4 plus, and then the Cl minus. And we know it's going to form P3N3Cl6, and it's also going to form HCl. So again, they haven't told us it's so we don't need to worry about it. What we need to think, okay, we need to kind of fit what we have into this molecule here. So I'm just thinking, okay, we're going to work from this random compound that we got given, the confusing looking one. So it has 3 phosphorus, so I'm going to put 3 here. Cool. It's got 3 nitrogen, so I'm also going to put 3 here. Now, in terms of chlorine, because obviously the other compound has chlorine, I'm just going to see how do we now balance the chlorine. So on the left-hand side, we've got 3 times 5, 15, plus 3, 18. Yeah? So because we have 6 in the molecule here, I'm thinking, okay, 18 set to 6, we've got 12 left. So I'm going to pop a 12 here and hope that now the hydrogens are balanced. So I can see in the ammonium chloride, 3 times 4, 12, yeah, balanced, cool. Happy with this. Now, no percentage by mass of phosphorus in this compound, I need to just know, okay, what is the MR of the compound, yeah? So if we work out the MR, we're doing 3 times 31 plus 3 times 14 plus 6 times 35.5. And my total is going to be 348, yeah? And then all I'm thinking, okay, 31 times 3 divided by 348 and then times it by 100 will get me a percentage composition by mass. And we just have to note as well 2 decimal places, so always remember to see that. And we're going to get 26.72. Okay. Now it says one example of evidence to show that this compound has a Kekule structure rather than delocalized. And literally again, you're just thinking, okay, well, we know what the evidence for the delocalized structure of benzene is. So in order to kind of rep the Kekule model, we're just going to say the opposite. Yeah, I hope that makes sense. So like, for example, in the delocalized structure, it's electrophilic substitution. Yeah, it's the bond lengths are all the same. The enthalpy of hydrogenation is less exothermic. So you're just reversing those points. Yeah, pretty much that. Cool. Now, finally, we need to suggest a structure. So if we're saying we're using the Kekule model, I'm going to think, okay, I want a cyclic structure. And we need to try and make all the nitrogens bonded to the phosphorus and the chlorine bonded to the phosphorus. Okay. So what I'm just thinking is, well, if we want a ring of 6, I'm more than happy to use those 2 as a ring of 6. So that's what we're going to do. We're going to do it alternating. So this is going to be nitrogen, then that's going to bond to phosphorus, that's going to bond to nitrogen, that's going to bond to phosphorus, and that's going to bond to nitrogen, which is going to bond to phosphorus. So not a perfect hexagon. We can kind of see, okay, in that, are the nitrogens bonded to phosphorus? Yes, they are. All of them are. Okay. And then what you're thinking, okay, with the chlorine, wow, if they're all going to be bonded to phosphorus as well, surely this makes the most sense. So I'm just going to double check that that actually works out. So we've got 2. So phosphorus has 5 in its outer shell, by the way. So 2, 3, 4, 5. Yep, fantastic. 2, 3, 4, 5. Yep. and 2, 3, 4, 5. Fantastic. So I'm more than happy with that molecule. And we're just kind of thinking, okay, if it's Kekule model, I'm just going to kind of work off that. Okay, so let's get the context of this question. So we're doing thin layer chromatography, right? They're using propan-1-ol and the reaction mixture. So if we're doing hydrolysis of 1-bromopropane, you will produce propan-1-ol at the end. That's what we're trying to aim to do. Yeah? So you can see here, let's just understand what's going on. If we have a propan-1-ol spot, that's to show us when the reaction is complete, the reaction mixture should just be propan-1-ol. Yeah? So because of that, that's why we're using propan-1-ol. That's something that's important to know. So you can see here, reaction is complete after 30 minutes. Cool. So if we are determining the retention factor for propan-1-ol, what we need to do is we need to get our rulers out, yeah, and we need to measure the length of this line from the origin to the solvent front, which happens to be 9.1 centimeter, and also we need to measure the line from the origin to propan-1-ol, yeah, which is 1.4 centimeters. So in terms of your retention factor, what you're then going to do is you're going to do 1.4 divided by 9.1, and that should give you your answer, yeah. So your answer is going to be 0.15. 0.15. Yeah. So I have a tendency to shout. Okay, equation for alkaline hydrolysis of 1-bromopropane. So because it's alkaline, and we're talking in the context of making alcohols, we know that we're going to use OH minus. So the structures of organic compound, again, I like using skeletal. So we've got that. Actually, I like using skeletal, but you know what? For your sake, we will use displayed because it is easier to follow. So you can see here, and then we've got the Br here. So that's 1-bromopropane adding the OH minus. And then we're going to form propan-1-ol. So this OH, adding the hydrogens as well. And then you're going to want to remember, okay, we replaced the bromine, so we're going to have Br minus. Yeah? You need to remember that. Cool. Now we're investigating alkaline hydrolysis of 1-chloropropane using the same method. Yeah. So they said particular reasons how the appearance would change after 20 minutes. So I'm looking at 20 minutes again and I'm saying, okay. So at 20 minutes, I can see here that we have got some propan-1-ol, but we also have still some of the 1-bromopropane. So what we're thinking, okay, the main difference between bromopropane and chloropropane is going to be the strength of the chlorine to carbon bond or the bromine to carbon bond. And chlorine has a smaller atomic radius, right, than bromine, so it's going to have a stronger bond, which is going to be harder to break, so it's less reactive. Yeah, reactivity is going to increase. So yeah, it's going to be less reactive because that bond is harder to break. Cool. So in terms of that, that means what we're going to say is that if we're looking here, if the reaction is slower, right, this top spot is going to be bigger. That's what we know. The top spot is going to be bigger. And also, in turn, this bottom spot is going to be smaller. So we can say one of those things. Either the top spot is going to be bigger or the bottom spot is going to be smaller. Reason, because we're suggesting why. That's what the question prompt is. Reason is because the chlorine to carbon bond is stronger than the carbon to bromine bond. So more energy needed to break it, so it reacts slower. Yeah? Cool. Then, why is propan-1-ol? So, it's a predictive reasons, that's why we said this. Now I'll suggest why propan-1-ol is used. Well, because we need to know when the reaction is complete. So as you can see at 30 minutes, yeah, you can see that we know the reaction is complete because there's no other cycles. We just have propan-1-ol in the reaction mixture, and we can compare it to something that we know is propan-1-ol. So that's the same kind of reasoning that we're doing. Okay, this is the last question, I believe. So we've got structural isomers, right? And they said that we have test tube reactions, yada, yada, yada. And then you can see the results of the test here. So our first question before we get into like the real nitty gritty of it is the formula for the species and the colors after causing the colors after reflux. Now, this one is just kind of knowledge that you should know pretty much. So what you should know is this is Cr3 plus, and this is going to be the dichromate ion, Cr2O7 2 minus. That's just knowledge that you should know. Cool. Now let's get into the question, the big one. So it says that we have further information. They are all isomers with that molecular formula. Cool. One of them is alicyclic. The other ones are unbranched. Cool. Now, what we're thinking, okay, how do observations provide evidence and suggest possible structures? So we're going to do this logically, starting with F. Now, we just need to know what we're identifying. So 2,4-DMP, it forms an orange precipitate if you have a carbonyl group. Acidified potassium dichromate, well, it's going to turn green if it has a primary or secondary alcohol. Yeah, or even if it's I think aldehydes as well. Aldehyde as well will form that reaction. Bromine water detects the presence of a alkene or a carbon-to-carbon double bond, and tolerance reagent identifies aldehydes, forms a silver mirror with an aldehyde. Okay, now we've got that down, we can start working. So F has an orange solution, so we know this does not have a carbonyl group. Yeah, if it's green, then we think, okay, well, we said green meaning it's a primary or secondary alcohol, but this one can't be an aldehyde because it didn't have the carbonyl group. So we think, okay, primary or secondary alcohol. Colorless solution. So if it decolorizes bromine water, that means that it does have a carbon-to-carbon double bond. And with Tollens reagent, it's colorless. So as we expected, it's not an aldehyde. So what we just know about F is we can write it down. So with F, we're saying that, well, the major pieces of evidence is that it decolorizes bromine water. So given that it decolorizes bromine water, it means that it has C double bond C. And we also know that, sorry about that, it forms the green solution, yeah. Green solution on reflux. So that means it's a primary or secondary alcohol. Yeah. So literally in that case, I'm kind of happy to just draw this whatever. So we know it's got a chain of 5. So literally with F, I'm just gonna do 1, 2, 3, 4, 5. We said it was unbunched, right? It's got a double bond in here somewhere, and it's also got an alcohol group. Whatever way you want to draw it, I'm happy with that. Yeah. You could draw this as a bunch of different ways, but that's one of them. Okay. Let's go to G. So G is also an orange solution, so it doesn't have a carbonyl group. Green solution, so it's a primary or secondary alcohol. This has stayed orange, so it does not have a carbon-to-carbon double bond, and it also isn't an aldehyde. So we're just thinking, okay, well, we know that G, the positive finding was the green solution on reflux. Hence, it must be a primary or secondary alcohol. That's all we know about it. It doesn't have anything else. So I'm thinking, okay, this has got to be our cyclic compound. I said one of them was alicyclic. This has got to be it. So I'm just thinking, okay, let's just draw that out. So apologies, let's do it properly. But let's do it this way. And then I can put the thing there. So that's going to be that. Yeah, happy with that. Okay, let's go on to H now. So H forms an orange precipitate here, which means it contains a carbonyl. So this is either now an aldehyde or a ketone. Yeah, I'm also saying, okay, it actually doesn't form anything. So it doesn't form the green solution with acidified dichromate. So it's not an aldehyde. So given that, it's got to be a ketone. Orange solution means it doesn't have a carbon-to-carbon double bond. Tollens reagent, colorless. So that means it's not an aldehyde, so it must be a ketone. So our finding with H is that it's orange precipitate with 2,4-DMP. So it has this, but we can say like no silver mirror with tolerance. So it must be, and also you could maybe add in the fact about the reflux as well. So it must be a ketone. So in that case, I'm happy to basically draw out any ketone with 5 carbons. So 1, 2, 3, 4, 5, and then we'll just put it here. That could be H. Now finally, we're going to use the extra space for I. So with I, let's just look at it again. Orange precipitate here. So because it's got an orange precipitate, it's got a carbonyl group. We're also thinking green solution. Okay, wait, but it had a carbonyl group. This must be an aldehyde, I'm thinking. Okay, bromine water, it doesn't have any positive finding there, so it doesn't have a carbon-to-carbon double bond. Tollens reagent, silver mirror, I'm like, okay. Well, immediately I'm just going to say silver mirror with tolerance. And that's pretty much CHR. That's pretty much an aldehyde. So then I'm just going to draw the only aldehyde we can form from this. So that's 5 and then double 1 O. And then that should be your answer for this.
Okay, and that is a wrap for this video. So I hope it's been really useful in terms of understanding how to approach these questions. It's the end of the chemistry papers, so good luck for your exams if you're doing it. Any questions about anything I've said, drop them in the comments below. If you found the video useful, please like and subscribe to the channel. We've also got our TikTok and our Instagram, both at OCR demola. Links hopefully should be in the description below. But I'll leave you to your revision. Have a good one. Bye for now.